actually made sense in math, right? That's some weird, crazy stuff in 3 dimensions and planes, which gets much harder. Okay, so let's suppose we're given a curve, some arbitrary curve. Let's say this. And the question is, if we zoom in on a single point on this curve, let's suppose this point right here, and we just zoom in, zoom in, zoom in, zoom in, right? Just like a microscope. And we find the tangent line. Right? And then from that tangent line, we can find the curve using a linear approximation, right? Way back in the day, right? It was linear approximation. It was a derivative of the portions, and that was called the linear approximation, meaning we can approximate the entire curve based off that point and that linear approximation tangent line. Okay. Well, guess what? We can do the exact same thing happening here in 3 dimensions or in space plane. Okay. The only difference is it gets a little bit more complicated of the picture. And I'll give it a surface and a point. And again, we can find curves. So we've already talked about this. You can find curves C1 and C2, and then find its tangent lines at that point. This is like T1, actually, yeah, and T2. And now, if we connect this, meaning if I make a actual plane based off these 2 vectors, that's what's called a tangent plane. And that's what we're going to be using to approximate the entire surface, hence called a linear approximation. The good thing is it's a linear function, so it's not that difficult to deal with. Okay. But the cool thing is this entire plane right here of this tangent plane represents the entire tangent lines through this point, meaning if I make another curve here, C3, and if I find its tangent line, it's also on the tangent plane. So it contains the entire tangent vectors through that particular point, and I can go all the way around the entire surface covering it, which is pretty cool because again, we could approximate the entire curve by just simply finding its tangent plane. Yeah. So therefore, we could define something pretty nicely. Suppose f is continuous partial derivatives, right? We know what partial derivatives are. An equation for the tangent plane is something we've already done so far, where z is equal to f of x and y, and given some point P in our surface, our tangent plane is equal to exactly this. So it's the partial derivative of x at the point, and the partial derivative of y at the point, and it's just z minus z naught, the point there. So we don't take the partial derivative of z. So very similar to what we did earlier, right? Just a tangent line itself. Now, if you're wondering, just in case, this was our usual suspect when it came to approximation in 2D. So just y minus y naught and the derivative of f, which is, very, very similar. Now we just do it in multidimensional. So it's a nice little template, goes back and forth, right? Okay, so now that we have a new definition, let's apply it. So find the tangent plane of the equation z equals 7x squared plus 4y squared at the point 1, 0, 2. Okay. So first, before we do anything, we need to find 2 derivatives. Derivative with respect to x and the derivative of f with respect to y, because we need them there and there. Okay. So derivative with respect to x, keeping everything else constant, so that's constant, so it goes away. So this can be 14x with respect to y. That's a constant, so it goes away. So we just get 8y. And now we plug them into the point 1, 0, 2. So plug in x, y to be respectively 1 and 0. So this ends up being 14. This ends up being 0. All right, so now we plug into our equation. So it's going to be z minus z naught, so minus 2, is equal to 14 times x minus 1 plus 0 times y minus 0. Or simplified. Like that. And if you really want, you could do some algebra and manipulation to do so, but it really doesn't matter. Either way is fine. Now, what's actually going on? So the linear approximation in single variable is the exact same as multivariable. Is if we zoom in on any type of curve itself at the derivative, and if I just zoom in as much as I can, this curve ends up being exactly the line, right? Hence the reason why we can actually approximate it. Same thing applies in a multivariable. Is given a surface S and its tangent plane T. Eventually, if I zoom in close enough, right, break it down, this curvature of this surface S ends up being almost identically to the tangent plane at that particular point. Okay, so if we take the entire points, right, the sum of all the points in every single tangent plane, that pretty much gives us S back, right? Or it's a good approximation of what S would look like. So that's essentially what's actually happening here. So that's the theory behind this linear approximation in multivariable. So now let's go back to the last example we had earlier. So it's this point here. And we had our tangent plane, and this is supposed to be 12 there. And our tangent plane z equals 14x minus 12. Yeah. So what we want to do is, it's supposed to be 12 there. So according to the visual we had, we can approximate the point at near 1, 0 using linear approximation of that. That's going to be our linear approximation equation. So this equation is called the linear approximation f at the point 1, 0, or approximation. Or roughly, we could say this. Approximate any value very, very close to the point 1, 0. So how do we actually use this? So let's suppose we want to find a linear approximation of 1.1 comma 0.05. So what that means is I'm going to plug in the point into our linear approximation model. And we just find out what we get. We get approximately 3.4. So this is what this section is all about. Finding a linear approximation for the surface and then just evaluating or finding values very, very close to it. So let's try an example out. And this just gives us a quick little definition stating that we can do that. So if the partial derivatives f and y exist at the point and continuous, then they're differentiable at a and b, meaning, right, we can actually do it. They don't give us undefined definition derivatives. So let's suppose we want to show that f of x and y equals x times e to the xy is differentiable at 1, 0. Find the linearization there and approximate f of 1.1, comma, negative 0.1. So we can do the same thing we did in the last example. We're going to find two derivatives. So first one with respect to x, and notice we're going to have to do product rule here for that one. So product rule is, right, so let's call this f and g. So f prime will be 1 times g plus f derivative of this one. So derivative of the inside is chain rule. So derivative with respect to x is just y times itself. And then for y, again, do the same thing, derivative with respect to y only. So again, it's a chain rule. Derivative of this one is just going to be x. So it's going to be x squared e to the x. And now we just plug in the point 1, 0. So plug in 1. So we get, plug in 1 and 0. So this one being 1 times 1 plus 0. Plug in 1 and 0. That also gives me 1. So therefore, our linearization looks like this. So it's going to be 1 there we go. Oh, actually, it's not here. Not here. So distributing, bring it over. So here's our tangent plane. So therefore, if we want to find the approximation of that, we just plug it in. And there we go. So hopefully stuff not too difficult to do. Okay. Now we have something called total differentiable. Okay. All right. So total differentiable basically means is that the derivative is changeable independent. Okay. So for example, what's actually going on? So let's suppose I have a surface in 2D. Let's say there. And let's suppose at this point right here, we have a tangent line. And again, so we have this curve, y equals f of x, and we have this tangent line. So we'll just write some stuff down. So we have a curve. And we have its tangent line. Which is created by the linear approximation. All right, so let's see what's actually going on here. So here's my point here, and the x component is going to be the a value, right? This is a comma b, for instance. So if we take the derivative of this, with just respect, old-fashioned derivative, right? Something you already know how to do. Okay, so we want to figure out what's happening here. So that represents the change of y. So if we go back to arbitrary, way back to actual, the derivative itself, derivative meant like, right, if I'm given an alternate point here, eventually if I put them close together, we get the tangent line itself. So if I go from the distance from here to there, this is called dy, the change of y, from this point to that point. However, any arbitrary change I want is the actual change of y itself, right? So this is the rate of change. This is the change of actual y values itself. So now what's going on? So dy is the change or the change that represents the height of the tangent line delta y represents the change in the height of the curve. Okay. Now, because we have change of y's and dy's, we also have the same thing when it comes to x's. This is dx here. Okay. Well, the thing is, since we were taking the derivative with respect to x, the only thing that's really changing is the y values, right? The height of itself. So this is the interesting part, is the dx change, the change in the x values, meaning how this goes from left to right, is the exact same as delta x, just the change in the x values. Because if I go from here to here, Well, this is just a plus the change of x, right? I'm just adding an extra component to a to get there, to get to this point right here. So that's just the same. So this is the change of x. So what I'm trying to get to is this same process, which was way back in the day of how to do linear approximations, right? Using the exact same model is done in space, where all we care about is four things: dy, dx, the change of y, and the change of x. Because all those four things help us find the linear approximation. Okay. Now the good thing is this is the exact same way when it comes to space and surfaces in space. Because in order to find total differentiable, it's exactly that. And here's a picture to prove it. Now it looks more complicated, but it's the exact same process we just did above. Okay. So known as z or delta z, this is now, instead of y, the change in height. And then dz is the same process as dy above. This is the change in height of the tangent line, or in this case, the tangent plane. So this is pretty interesting because the exact same process we did earlier in Cal 1 and Cal 2 of how to find differentiables and itself applies here as well. But in space, we call it total differentiable. That's it. That's the only difference itself. So let's try an example out so you can see what this process is going to look like with some numerical instead of the theoretical. All right, so given the z is equal to x to the third plus 3xy minus y to the third, A, find the differentiable z, and then B, if x changes from 2 to 2.6 and y changes from 3 to 2.98, compare the values of delta z and dz. Okay. So we want to find the differentiable dz, and that's just right here. We're going to find the partial derivatives with respect to x and y. And just have dx and d theta there. So first, partial derivative with respect to x. So be 3x squared. That goes away because it's constant. With respect to x is just going to be plus 3y. Same thing for partial with y. This goes away, it's constant, so it's going to be 3x minus 3y squared. So according to our equation, our differentiable dz is going to equal to the 3x squared plus 3y dx plus 3x minus 3y squared dy. That's our equation for total differentiable. So now for part B, what this is saying is, okay, I want to figure out what dz is going to be, this approximation itself, using these 2 points. Okay, so notice the only thing we need to do, because we're giving it x and y, is dx and dy. So how this is going to work. So this is x and this is y, respectively. And now we got to find dx and dy. Okay. So dx is the change of x. So from this point to that point. So if we literally subtract, we get dx. And same thing for here. dy is the change of y from one point to the other point. So subtract this minus that, and we get negative 0.02. So now that we have all four numbers, respectively where they're supposed to be, well, not this one, but these ones, now we just plug them in. It's going to be 3, 2 squared, plus 3 times 3, times dx, which is 0.06, sorry, plus 3 times 2, minus 3 times 3 squared, I'm running out of space here, times negative 0.02. So just simplifying everything we have. So this whole part just gives me 1.26, and the other part gives me 0.42. So adding this together, our approximation is going to be 1.68. So now it tells us to compare it to dz, or change of z. Okay. So remember, what that means is all I'm doing is finding the change from one point to the other point. That's what we're doing. So if I plug in the 0.206 and 2.98 into our equation, and if I plug in the 0.23 into here, what's that change going to be? That's literally all it's saying. Okay, so I'll spare you the details. It gives us that, which you notice is very close to our approximation. So our model of total differentiable is a great model to show that it's a linear approximation given points arbitrarily close to the points 2, 3. Which is pretty nice. Or, in general now throughout this entire curve, which is the best part. So again, the key thing is this is total, hence why it's called total. It's not an actual to a single point anymore. It's the entire plane's itself curvature, which is really cool. All right. So why don't we do some applications based off this? So you can see how this is actually done in the life scenarios. Okay. So we have a couple examples before we go on. Two very interesting examples. So the first example, the base radius and the height of a right cylinder can be measured by 12 meters and 24 meters. All right, so just in case you're not sure, like I always like to do, I always just like to draw a picture. So we have a right cylinder. Here's my cylinder. And my radius there, right? Okay, so it says, so the radius is going to be 12. From here to here is 12. And the height is 20. Okay, so that's our little cylinder there. Okay, so given a base and a height of 12 and 20, with a possible error in measures as much as 0.01. So that's going to be interesting. Error 0.01. We'll see what that means there. Use differentials to estimate the maximum error in the calculated volume of the cone. Okay, that's interesting stuff, right? So we want to find dz at the point 1220, the change of z, right? Because we want the differential. Okay, so we have a volume of a cylinder is equal to pi over 3r squared h. Okay, so think of this as just like xyz. Okay, so in order to use our differential formula, we have to find respect to both variables. So we define the volume with respect to r and the volume with respect to h, right? Differentiate both. So volume with respect to r is just derivative of r squared, which is 2r. So it's going to be 2 pi over 3r h. And now derivative with respect to h is just going to be everything except the h. So now, according to our equation, we're just going to write exactly that. But instead of x and y's, we have r's and h's. So dz, or the change of the volume, I guess we could call it volume if you want, is equal to 2 pi rh over 3 times dr plus pi over 3r squared times dh. Okay, so this is our general equation. Okay. Now, the only thing we have not done or used actually is this weird error there. So let's see what this error represents. So it says with a possible error in measurements as much as 0.01. Now this error in measurements means is the change, right? Is the change from actual from what the error we got. So this error in measurements, or this change of the measurement, is exactly that right here. Because that's what happens when it's equal to the actual minus what we get, right? So that's the approximation we're looking for. So an error of no change of that. And since both the measurements are 0.01, each one of these is going to be 0.01. So therefore, we plug it in. So plug in 0.01 here and there, and we get approximately this. So this is the maximum error we can have based off our little simple error we had earlier. So 0.01 meters error can actually leave us a 6.54 meters error altogether. Pretty crazy, huh? So again, estimating is pretty good, right? So 6.54 meters sound like a lot, but it's actually not that bad. So let's try another one. Everybody's favorite boxes, right? So the dimensions of a rectangular box are measured to be 80 centimeters, 55 centimeters, and 40 centimeters. Each measurement is correct to within 0.3 centimeters. So again, each measurement. So we're going to know this is going to be our D something here. Use differentials to estimate the maximum error when the volume of the box is calculated for these measurements. What percentage of the error is it in the volume in general? Okay. So, like everything else, let's make a little picture of ourselves. So here's a little box. Okay. So it says dimensions is 80, 55, and 40. So let's say this is 80, 55, and then 40. All right. And it's told to us, I'll just write this down now. So DL is 0.3, DW is 0.3, and D height is 0.3, right? Because they told us all the measurements is within there. Okay, so now we go to a volume is equal to the multiplication of all three together. So since we have three different variables, that means we have to calculate three different derivatives. VL, VH, and VW. So the derivative with respect to L is just WH, with respect to H is going to be LW, with respect to volume is going to be LH, right? Keeping the other ones its constants. So now, instead of saying DZ, I'm going to write exactly what it's supposed to be. We'll say DV, that's the change in volume we're looking for, is equal to each one times its derivative. So WH times DL plus LW times DH plus LH times DW. And now we plug in everything we know. So W is going to be 2055, height is 40, change of L is 0.3, and just repeat, right? So plug in all the numbers we actually have, and we get roughly this for approximate. So just like the last question, so we could stop here, right? That's how much error we had for the volume itself. Now, which looks like a lot, just like it is here, right? 6.54 meters and 2,000, almost 3,000 centimeters is a big error, right? Like, holy moly, does this actually work? Because, that's a pretty big error. Can we even get even closer? Well, that becomes the reason why we do the next part of this section, this question. What percentage of the error is it to the volume of the box? Okay. So to do so, we want to find the percent error. So first we want to find the volume of the actual box, right? So without this kind of stuff. So literally just multiplying length times width times height. That gives you approximate or exactly this. And just in case you guys forgot or not sure, percent error is always equal to the error itself divided by the total volume we have times 100. So our error in this case is what we got earlier, and the bottom is the entire volume itself without any error. So then dividing and multiplying by 100, because we're in percentage, gives us 1.67%. So in the grand scheme of things, that's actually not that bad, right? So this is approximately a 2% error overall, which is pretty good. 2% is pretty good. If you guys see statistics, right? 5%, anything under 5% is considered perfectly fine, right? Which is 2%, which is way better than the 5% rule usually done in statistics. So fun little examples using differentials so you can see how it's going to work out. So, optimizing, minimizing, all that fun stuff, right? We wanted the maximum error we can have, minimum error, all this stuff is done using differentiables, right, in space, which is pretty cool, right? It's another alternative way to doing optimization problems. When it's, sometimes the optimization is pretty too difficult with the constraints and the objectives and things like that.